Hi everyone, we are Alessandra and Junyang, and our project is on high-performance large-scale regression. So first of all, our project was sponsored by CRAE, and it was developed in collaboration with the CRAE Europe, Middle East and Asia Research Lab, who helped us understand how to use best Eureka GX platform, which is a platform that is available on the Institute's supercomputer. The goal of the internship was to understand the current methods, algorithms, and libraries to do linear and logistic regression in distributed settings and how to use them on Eureka, and hopefully provide guidance to people in academia and industry on how to perform linear regression with very large datasets. We also analyzed a dataset containing the information about all the flight delays in the US from 1987 to 2008. So this is a good example on how to do linear regression in large settings, but it can also help airplane companies understand why delays happen and which are the variables that influence them most. So how to do regression on Eureka? There are many ways to do it, but we've focused mainly on Apache Spark and TensorFlow. Apache Spark and TensorFlow are both very popular libraries at the moment for machine learning. And Apache Spark is known for handling well in-memory data very quickly and sharing memory and computation power between nodes, whereas TensorFlow is a library developed by Google, where the underlying assumption is that the data that you're using are too big to be loaded into memory. So what it does is that it loads batches of data at each time. On Eureka, there are many nodes with 36 CPUs each. And the great thing about the platform is that we can run multiple jobs at the same time, and also that it has a user interface where we can see in real time which CPUs we are using.
Okay, so when you run a job in Spark, the main settings that you want to take into account are the following three. So the first, so it's the maximum number of cores, the number of cores per executor, and the memory per executor. And all of this can be controlled through Mesos inside Spark via some sort of API. So we use Python, but you could use Scala, Java, R. So there's a wide range of options available. And what Mesos does basically is it controls how a job, basically how your code is run through like a cluster of computers. And it does so mainly via these three settings. So Eureka, for instance, it has 36 CPUs per node and 9 available nodes. So a node is like a computer inside a cluster, and it also has about 200 gigabytes of RAM available on each node. So in total, this makes for about for exactly 324 nodes in which we can run in parallel for any job. So for the fastest performance, we want to use all of the cores, but there is one restriction we have to take into account, which is that the total memory is only about 1,800 gigabytes, which just comes from the fact that each node has about 200 gigabytes of RAM, and you've got 9 of them. So basically, you want to give. So like I said, one of the important variables you have to sort of set yourself is the memory per executor. So you want to set this so that the total memory doesn't exceed around 1,800 gigabytes, because otherwise Spark will start to reduce the number of cores it runs on automatically because it hasn't got enough memory, basically, and that usually slows down the algorithm. So memory per executor should be kept below 200 gigabytes in the case of 324 cores, and this is just a general formula to demonstrate how like a relationship between the three above variables. When sort of choosing the parameters you want to run. So for example, so basically the idea is your number of the number of maximum cores, which is capped at 324, divided by the number of cores per executor, times the memory per executor should be less than equal to about 1800. It's this one, okay. So this is like an example benchmark of linear regression in Spark. So largely we try to do benchmarks under two sort of settings. One is large N and small p. So this is when you have a data set with a very large number of rows, but not very many columns. And the other way around, where you've got a so I appear to have said the same thing, small p, large N. Yeah, it's meant to say large p, small n. My apologies. And all these tests were run under the maximum number of cores. So so you can see for large N and the data in this case is multivariate normal, just synthetic data generated randomly. So in this case, you can sort of see that for large N and small p, Spark performs pretty well. So so even at 10 billion rows and 100 columns, which should be more than enough for the vast majority of even big data applications, the code takes about 32,000 seconds to run, which is 8 to 9 hours. So it still takes a while, but it's runnable. But for data sort of for example, for 1 billion rows or for 100 million rows, it should run within a few hours or even just I think that's within 4 minutes for 100 million. So that's pretty good. For large P, however, things are more difficult because linear regression for large P needs to have some kind of penalization, otherwise the solution doesn't exist. So here we use the L1 penalization or lasso, and you can see here that for relatively small, well, I say relatively small, but still a very large number of columns, right? You still got 100,000 and 1 million columns. In those cases, it takes something like 2,000 to 3,000 seconds to run, which is about sort of 40 minutes to an hour. So so I think the L1 penalization really slows it down for very large columns, unfortunately. And for 10 to the 7, I think either the code takes so long or it doesn't, or it's running out of memory or something that we can't really get a result in reliable time. So this is just this is another benchmark which compares the time versus the number of cores that you're running on. So so the data here is fixed. So we just fix it to have 100 million rows and 10 columns, and also 100 gigabytes of memory per executor. So so in this case you shouldn't exceed it because we have so this only used about 900 gigabytes of memory, which is only about half of the maximum limit. So here you can see that so the number of cores, increasing number of cores does have a pretty big impact on the speed, but it sort of plateaus off as you'd expect after sort of maybe around 200 cores. But obviously for larger data sets, this would be sort of having a higher number of cores would have a more noticeable impact. But this is just to give you an idea of the impact of increasing the number of cores and the general value of having a system like Eureka GX, where you have a lot of cores which you can run something like linear regression in parallel.
Thanks. So for TensorFlow, I'll just give a very brief introduction, and then we'll explain which are the pros and cons of using TensorFlow. So first of all, the core TensorFlow is written in C++ and Python, but then there are some building blocks that are ready to use for anyone, which are layers, losses, and metrics, and so on, that you can put together to build your own model. But there are also these estimators, which already include everything you need for most machine learning methods. So we're going to focus on these, and this is because linear and logistic regression are already implemented as estimators, and they look quite simple to use. So for example, if you define your input functions, then instantiating a classifier. So for logistic regression, it's just 2 lines. Just have to tell it which columns you want to use. And then training, evaluation, and prediction are 1 line each. Also, there are many variants of stochastic gradient descents implemented in TensorFlow, so you can choose any of those. You can set different penalties. And as I said, there's no need to load the data in memory. And also, TensorFlow detects automatically which devices are available and is able to automatically decide which computations are being done by which devices. However, we found some difficulties using TensorFlow because in our case, we found that it lacked some basic functionalities. So for example, running a linear regression with a large number of covariates, so large P, the output is the output of the weights, so the coefficients of the linear regression is just a list of coefficients where you don't know which value corresponds to which covariate, which is a bit counterintuitive if you think that this is like the coefficients of the regression are quite important and quite an important output of regression. Also, the computation time is linear with a number of data points, but it explodes with P. And finally, for distributed TensorFlow, so you can start multiple workers at the same time. But what we found is that, for example, here in this figure, I'm showing what happens when you start 3 workers on one node. And the problem is that 3 workers only use 25% of one node. So if you want to use all the researchers on Eureka, you really have to start lots of workers. And the problem with that is that you really have to specify each worker 1 by 1 and each port 1 by 1. And your MRun job will look something like this, only for 8 workers. So that is why we don't have results for very large regressions such as we have for Apache Spark. Finally, the airline data. As I mentioned before, we have information available for all the flights between 1997 and 2008 in the US. So that is 120 million records in total. And for each flight, we know the date, the arrival and departure times, the carrier names, the flight name, and the origin and destination airports. Some of the questions that we can answer with those data are what is the best time of the day or the week or the year to fly in order to avoid delays, and which are the airports that are more affected by delays.
Right. So a brief introduction of how we set up the logistic regression problem. So the idea is we want to predict whether a flight is delayed or not, but sort of only using the information you know before the flight actually takes off. So the training data is recorded between 1987 and 2007. So this is about 112 million rows. Test data set is we just used for the data in 2008. So this only takes about 15 minutes to train with lasso penalization on Spark. So, you know, it's pretty fast. In R, for example, if you, within the same amount of time, you probably train a data set with about 30,000 rows or something like that. So, you know, this is a clear improvement in terms of the scale of the data set you can work with. And after some feature engineering and sort of expanding out the factor variables, because in Spark you kind of have to work with factor variables in terms of indicator functions of each of the sort of category you've got in your categorical variable. So the data in the end contained about 780 features or columns, and this is just a model formula to give you some idea of the variables involved. So so these sort of CRS times are basically the expected time. So the CRS arrive time, for example, would mean the expected time for the plane to arrive, and we also have other things like what month it is, the day of the month, the day of the week, the unique carrier ID, what airport the plane took off from, and the destination, and so on. So to summarize the model coefficient and findings, we found that the months most likely to contain delays are December, January, June, and July, which is kind of what you expect, right? Because this is around the winter holidays and also the summer, and September and May ended up being the least likely. Friday and Thursday are most likely to contain delays, while Saturday and Sunday are least likely. It's somewhat surprising, but maybe not that. Maybe there is a reason why Friday and Thursday is a bit busier than other times. And also we have sort of a list of airports that where sort of delays are most likely to happen. And there is a little bit of overlap between between flights, or like the airports which flights originate from and the airports which the flight arrives from, which indicates that some airports might be more prone to delays than others. And in terms of the time of the day, we found that delays are most likely between sort of the late afternoon and evening, which makes sense because the general advice when taking sort of airplanes is to get there early to avoid delays, and it's least likely between 4 a.m. and 9 a.m. And also over time, delays have become less likely in recent years, which is good news. So this is the precision and recall plot. So recall is the number of true positives you've managed to predict divided by the number of positives there actually were in the original data. So in this case, it would be how many delays your model managed to predict correctly over the number of delays there actually were in the original data. Precision is the number of true positives, which again is the number of number of delays you've managed to predict correctly over the number of delays your model actually predicted. So basically the intuition is when recall is 1, that's basically when you're So this curve is generated because logistic regression gives you like a continuous output. So you have to define a probability threshold to say, okay, if the probability is over 0.5, we're going to say that's a delay. If it's less than that, we're going to say it's not a delay. So at the bottom, for when recall is 1, that's when you can think of that as when your probability is 1, and then you sort of and then when it's 0, that's when you say, okay, I'm gonna when it's 1 is when you say you predict everyone as delays, and when it's 0 is predict none of the flights are delays, and everything in between is like a continuous sort of increase of your threshold for the probability of delay. But basically the model is not too predictive. It's not too much better than a naive model. But I think in this case it might be to do with the limitations of the data, because I also tried running this with more sophisticated models like random forests and also SVMs, and I didn't really get an increase in sort of predictive power. So, but I think the point here is to illustrate that we can indeed run, at least in terms of speed and being able to run these models on very large data sets is very doable in Spark, even on sort of realistic data sets.
Thank you. I think we are out of time, so I'm just going to say that the main output of the internship will be a blog post explaining our findings and how to do linear regression on Eureka GX, and also using the airline data as a running example. And we will also make available our report online and our code as well. And just wanted to thank everyone here at the Turing and also at Cray for their support throughout the internship. Thank you.